So in the last classes, we try to really look at these mathematical formulas, how to really quantify something like the velocity field, what we see if we are going to do an experiment. Maybe it might be a wind turbine blade or your fan blades, gas turbine blades, jet engines. It can be even your inkjet printers, even it can be cooling of electronic equipment, whatever it might be. There always be associated velocity field when air is or perhaps fluid is moving over substances. And that variable, what we have addressed is u as a function of x and t, we can really measure. And this velocity field, it can be in x direction, y direction, z direction, depends on how this fluid is flowing. So we usually associate it with underscore to represent u is a vectorial field, and it depends on all x, y, z and t kind of coordinates. Based on the measurement where we are going to keep our probe or how we are going to visualize the things and so on, we can always construct gradients of velocity. Though velocity is a vectorial field, gradient applied on that going to give me second rank tensor. And this is a very fundamental quantity to understand any complex fluid mechanics problem. Engineering devices are quite easy to do or handle. You just crank it up like a repairman. Maybe I'm going to change this, I'm going to get that, and so on, so kind of thing. But that's usually not more like a logical deduction, other than just by practicing engineers what they try to do. Instead of that, the real scientists, what they have figured out, maybe mathematical expressions and so on, so kind of thing. First of all, give us more clarity and quantification of those objects. One of the objects central for fluid mechanics is this gradient u term. And especially this velocity gradient term, because it's a second rank tensor, one can really decompose into symmetric and anti-symmetric or skew symmetric kind of components. The symmetric part, grad u plus grad u transpose, half of that, which is half of del ui by del xj plus del uj by del xi. That's what we call symmetric part of the velocity gradient tensor, which tells us about strain rate information. Unless we have strain rate information, we will not be in a position to construct stress principles or equilibriums and forces, accelerations, and so on. You have to measure it to say this is the thing happening. The other part, skew symmetric part, del ui by del xj minus del uj by del xi with half of that term, what we usually call angular velocity of the system. Whether it is a fluid mechanics, whether it is a solid mechanics kind of problems, these principles are one and the same. And this del ui by del xj, del uj by del xi, if we are going to really look at, it will have components. First component, second component, third component. Rest of the things are zero. Because it's del ui by del xj minus del uj by del xi. Let us keep something like 1, 1, 2, 2, this kind of combination. What we will end up is, if we are going to really write it, when I is equal to j is equal to 1, then del u1 by del xj. So this entire component, what I am trying to write is this one. First component is 0, del u1 by del x1 minus del u1 by del x1. Now j increased to 2. That means what I am going to get is del u1 by del x2 minus del u2 by del x1 with half. Similarly, the next component really comes half of del u1 by del x3 minus del u3 by del x1. So such kind of cross components exist. And wherever you have principal diagonal, those elements becomes 1 and the 0, and you will have anti-symmetric part. That means this one repeats with minus sign and this one repeats with minus sign. That is the way this entire structure really looks like. And from there, one can really show that some of the components can be connected with del cross U terms. We will see that when we are working out the examples. But as of now, what we can really see is the central part is gradient of U that under different kind of decompositions might give you strain rates and angular velocity and so on so stuff. And especially the symmetric part, whatever we are saying, del ui by del xa, del uj by del xi, usually connected by two further components named linear strain rate and angular strain rate. We have already seen linear strain rate means in this entire information, this one is linear components and angular components are the crosswise components. That way one can further decompose this symmetric strain rate tensor. And usually this Q symmetric part gives us rotation rate, which we call in some sense angular velocity of the system. Especially in that rotation rate, one of the first fundamental quantity is called vorticity. Vorticity is the one which we define as del cross U. This is the way you quantify, you measure velocity, you simulate it, experimentally you find it, try to figure it out everywhere U and figure it out what is that curl. Later we will see when we are learning about Newton's equation, Navier-Stokes equation and so on. This vorticity actually forces your fluid to go from one location to other location to develop into instabilities and turbulence. If I look at microscopic view, you have a lot of complicated flow field. Pick tiny elements, infinitesimal element, you pick it everywhere. Because we are on Cartesian coordinate system, I always draw something like rectangles. You think of each of that trying to have some tiny rotation about its own axis. If that is happening, we will call it possess vorticity at local level. All these things, if I am going to really include that, I may be generating vortex flow. Maybe. Why I'm saying maybe, we will see. Whenever such kind of motions exist, rotations, usually such kind of rotation, you will be generate by applying shear forces inside the system. For example, initially there is a black element, but because you apply, it start trying to spin around, it translates and also starts spinning around its own axis. It may not be complete spin, but even a kind of spin, if it happens, we will call it as vorticity. For example, in the last videos we have seen there is a flat plate, flow comes past over that. So any fluid particle try to spin around its own axis, very next to the plate, and you start developing something like boundary layers. The way we quantify that is del cross U. Fine. There is a global effect of this vorticity, what we call circulation. Again, another mathematical term. You take your U, integrate around certain closed path. Closed path means maybe this is the aerofoil. Flow really comes in this direction. Flow passed over that aerofoil. Then you are trying to take something like a circuit. Circuit, let us pick something like a red color. This is the red line, is the object under consideration. Along that line, pick what is U components. Try to look at U dot dl around that line. Is good enough to calculate what is overall nature of the flow. Let me put it once again. You might be going to take aerofoil. You want to understand what is happening with the flow features. I don't have to really construct throughout the aerofoil, find out the measurements. What I can always do is, this is my aerofoil. I can really put some probes here, 1, 2, 3, maybe 4, 5, 6, 7. These points are good enough for me to really get information of the velocity field, because I'm going to keep probes around these aerofoils, which aerofoils are kept in these wind tunnels. Try to understand what is the lift, drag force acting on that, and so on. In olden days, I'm talking about in 1940s, 50s, 30s kind of thing, where sophisticated cameras, visualization techniques were not very much developed. Now, if I want to really find out what is the drag acting on that, lift acting on that, why it is acting, and so on, so kind of stuff, I don't have to really measure everywhere. Maybe keep these 7 probes. Just measure what is the velocity information. What is the velocity information? What is the velocity information? What is the velocity information? Velocity information, velocity information. This is good enough, these 7 points. Now I know where 7 points are there. Now try to connect by a line. Arbitrary line. It doesn't have to be so accurate line. Just say arbitrary line. That arbitrary line, what I'm showing here as a contour, let us think of. It might be having finite number of some 7 or 8 probes around aerofoil. It can be even around car. It can be even on any object. Calculate U dot dl around that particular line. And that entire integral effect around that line, what we call circulation. And by your Stokes theorem, the circulation, the vorticity integral value are directly connected with each other. If I again repeat the same thing, vorticity is a fundamental thing to understand any fluid mechanics problem. That is the one which tells you drag, that is the one which tells you rotational events, that is the one which tells you lift, that is the one which tells you how you can really tweak it to get desired effect like lift, drag, and mixing, and so on, so kind of stuff. So now the question really comes into picture. Can I really measure vorticity directly? At math level, it's quite easy. However, doing an experiment trying to measure vorticity inside the system is not trivial task unless you have sophisticated tools to visualize it. In present day, you can do that. But the course what we are learning is something like 19th century and so on. We are moving towards 1950s, 60s kind of boundary layer theory. That is the way we are evolving. So this vorticity, when they have really figured out by math guys in the 18th century, they do not have any sophisticated tools. I don't know even whether chimeras really exist or not, but you can always measure velocity by hot wires, by calibration, Wheatstone bridge and so on. What they try to do is, around the objects, you put some probes here and there, calculate velocity. Once you know velocity, because I cannot measure vorticity curl everywhere inside the system and so on, so kind of stuff, what I can do is calculate this circulation around the object as U dot dl at finite number. If I calculate the integral value, that based on the Stokes theorem supposed to give me vorticity. If I know vorticity, I can calculate any other things. I can manipulate anything. That is the way mathematically they have tried to really define this circulation concept. Is that clear to everyone? And this is one of the fundamental quantities for aerodynamics, guys. Whoever so studying aerospace engineering, aerodynamics, and so on, so kind of thing, circulation becomes very, very fundamental thing, even compared to vorticity. Because if you can know this finite number of objects, you are done with your problems. You can manipulate the things. You can get the desired effects. And there is one more concept named velocity potential. When we are working out examples, we will learn more about that. The velocity potential basically defines whenever you have vorticity is equal to 0 inside the system. That means there is no spinning happening. That happens for something named inviscid flows. Whether it possesses viscosity or not, but if vorticity is equal to 0 at a given location, we call such kind of flows as inviscid flow. Mathematically, del cross u becomes 0, you will call inviscid flow. Why we have to learn about that? It might be very beginner's course at this level, but when you go to study aerodynamics and so on, advanced fluid mechanics kind of courses and so on, most of the flows away from the boundaries, that means away from the fan blades, away from the gas turbine blades, away from the rocket nozzles, away from your computer chip cooling and so on, so thing, wherever boundaries are excluded, most of the flow behaves like inviscid. When that happens, calculations become so simple to handle it. Otherwise, we have to solve Navier-Stokes equation with your initial condition, boundary conditions, which are non-trivial tasks. But when this kind of inviscid flow exists, means your curl of vorticity, you are confirming this is 0. Your big equation drastically reduced to very small equations, which are much easier to solve very quickly. For the purpose, we are going to learn about this velocity potential also. Whenever del cross u is equal to 0, one can really write that mathematical function velocity field as a gradient of scalar potential. So that if I am going to take del cross of that scalar potential phi, it naturally becomes 0. That means your vorticity, because this is del cross u, what we have defined as vorticity, that becomes 0. That means this function phi, one can really associate name as velocity potential. Right now, we are just learning terminology. Don't worry about applications. When we are working out examples, you will learn about why I really need that. But at one point, we have to learn about that terminology, and we are learning. Okay? Guys. Hello?
Yes, sir. Yes, sir.
Okay. And when you are going to learn CFD, computational fluid mechanics, this velocity potential becomes one of the basis. Most of the aerodynamics problems, they don't solve Navier-Stokes equation. They solve something named Euler equations, where your vorticity is already chucked out. In that case, this velocity potential becomes very friendly to handle, get the information. Think of, instead of solving a vectorial field, you are going to solve a scalar field. Handling scalar field where only one component throughout the space time is much easier in terms of storage compared to a vectorial field, which in terms of space, 3 components one has to handle. That kind of added advantage what this velocity potential gives us. Similarly, there is something named stream function in 2D. Especially for incompressible flows, that means you take any fluid particle, its density doesn't change. For fluid particle, you cannot really squeeze it, you cannot really compress, elongate it, but you can deform it. That means you take something like a balloon, air balloon, you try to squeeze it. As long as volume is not changing, but it is going to have dimple, stretch, and so on. This one, when I'm going to really make it like apply force, the volume of this The volume of this one and the same, but it is just get deformed. Such kind of flows, what we call incompressible flows. It can really stretch and so on, so thing. But initial volume, final volume of that particular fluid particle, if it remains same, we will call incompressible flow. The condition for that we have already seen. Fluid particle means material derivative, the overall derivative, the total derivative, the substantial derivative, the Lagrangian derivative, the synonymous names. D by dt of the fluid particle for density not going to change. That kind of systems, what we call incompressible flows. Especially in 2D incompressible flows, d rho by dt is equal to 0 means my del rho by del t plus del dot rho u is equal to 0. And because this rho is not varying, one can show that del dot u is equal to 0 for incompressible flows. But incompressibility condition means your capital D rho by dt is equal to 0, which ultimately turns out to be on the Eulerian field, divergence of u is equal to 0. If that is the case, one can always introduce something named a stream function psi, such that velocity u can be written in terms of the stream function del psi by del y and v is equal to minus del psi by del x, such that if we are going to write velocity field as del psi by del y and minus del psi by del x and divergence of u del by del x of del psi by del y plus del by del y of minus del psi by del x, both really get cancelled out to give you divergence of u is equal to 0. That means whenever you have divergence of u is equal to 0, one will be in a position to really introduce something named stream function. So at your CFD course, you solve Navier-Stokes equation in terms of your stream function and velocity potential coordinates. That becomes so easy to handle. We will learn when we are going to learn about this velocity, when we are solving this Navier-Stokes equation at one of our CFD lectures. There, I will introduce something like stream function vorticity, stream function velocity formulation. For that purpose, again, we require these mathematical tools named velocity potential, where velocity potential phi defined as u is equal to grad phi, and stream function is defined as u is equal to del psi by del y and v is equal to minus del psi by del x. So first of all, let us look at few examples so that you will have reasonable comfortness in terms of this vorticity field. So let us begin. Your velocity field, when you are doing an experiment, you have figured it out. 3xy square I plus 2xyj plus 2zy plus 3tk. And I would like to know vorticity at some space 1, 2, 1. That means you have something like x coordinate, y coordinates, z coordinates. Somehow through your cameras or simulations, whatever that, you have flow field. At kinematics, you will describe flow field by different things. Maybe some of them is streak lines, some of them by streamlines, some of them by looking at directly velocity vectors, some of them by vorticity vectors and so on, so kind of stuff. Because here we know velocity field, we are interested to calculate vorticity. Vorticity is defined as del cross u curl of u, which is epsilon ijk del j uk. So we know how to apply epsilon ijk on del j uk. Del by del y of second term, and third terms, first terms and third terms, and then again first terms and second terms. We know how to calculate curl. If I calculate that, plug these numbers at 1, 2, 1, x is equal to 1, y is equal to 2, z is equal to 1 location, we will end up with 2ji plus 0j plus 2y minus 6xyk. At 1 to 1 location, the vorticity value is 2i plus 0j minus 8k. Vorticity exists, that means you start seeing curly motions. Something like such kind of curly motions you are going to see. You don't have to really plot streamlines inside the system. That is the advantage in knowing vorticity. Can you visualize that? Hello? Let me call by name so that it becomes easy. Amit. Is Amit here around? Amit Kumar?
Yes, sir.
So what I am trying to say here is, when you have velocity field, unless one really visualize streamlines, I will not really have visual feeling of that flow. By just knowing u value 3xy squared, 2xy, 2zy plus 3t, one may not be in a position to really visualize whether flow is going straight, laminar kind of thing, or having curly motions. Now, if I would like to really plot streamlines, it is non-trivial task because I have to really plot stream functions, streamlines as del psi by del y and v is equal to minus del psi by del x. Now, how I will be in a position to even construct that stream function? Maybe Niranjan must have tried it on his computer, which we will learn it. By knowing velocity field, he tried to visualize streamlines. It is not that obvious to plot it using computers. However, if you bring this concept named vorticity, it tells you, hey, you calculate curl of u. And at the end of the day, I'm going to really get this function 2z plus 0j, 2y minus 6y. And what I'm going to really do is take x coordinate, y coordinate, and z coordinate. What I'm trying to say, let us put instead of y here z because it becomes easy for me. This is z and this is y. Vorticity says that it doesn't depend on y direction. And it tells me 2z plus 2y minus 6xy at a given 1 to 1 point. If I'm going to pick 1, this is 2 and 1 here, the 3-dimensional thing. It tells me 2i minus 8k. That means if I would like to really plot it, the projected value here, what I can really do is supposed to have 2 units and it's supposed to have 8 units in the downward direction. That means my vorticity vector is that. That straight away I will be in a position to really visualize having something like a spin. So such kind of spinning events, I can so usually visualize it. That is the advantage of vorticity. Otherwise, unless I integrate throughout the field, I will not be in a position to visualize streamlines. Streak lines are more complicated to visualize and construct it. Experimentally, they are so easy to construct. But if I would like to backtrack them, it is not that easy to do. At computer levels, plotting vorticity is much user-friendly. Okay. Now, let us look at another example. Here, I'm going to ask you many examples like, can I calculate velocity gradient tensor, angular velocity, deformation rate, strain rate, and what is the change in angle between a fluid element having this dx, dy, and principal strain rates and directions. Okay, Let us look at examples. So we will have bit practice in terms of math. There is something like a velocity field, and these examples are bit artificial. We just would like to get little bit grip about maths. There is a reason we are picking up this kind of example. Okay. Now, if there is something like a velocity field, 3xy square I plus 2xyj plus 2zy plus 3t. I would like to calculate velocity gradient tensor. Can you help me out how to calculate that? What I'm supposed to do? Velocity gradient tensor is you take del, apply it on u. This is what we call velocity gradient tensor. It is a second rank tensor. So that means it looks like this. Del j ui r del I uj we have to calculate. So del u1 by del x1, del u1 by del x2, del u1 by del x3, and del u2 by del x1, del u2 by del x2, del u2 by del x3, del u3 by del x1, del u3 by del x2, del u3 by del x3. This entire template, what we call velocity gradient tensor. It is not divergence. Divergence means dot is there. You have to condense. So now if you are going to calculate del u1 by del x1, 6xy, del u1 by del x2, that means pick this one with respect to y. Del x2 we have to really do 3xy square, which we are going to do with respect to, I think I
So
made a
first term should
mistake.
be 3y square, I guess.
Right. I made a mistake. I'm sorry. Made a mistake. So let us do that step by step. So first one is del u1 by del x1. u1 is this component with respect to x, 3y square. Del u1 by del x2, I would like to calculate. Del u1 by del x2 is 3xy square. So with respect to y is 6xy. I will update the notes. Del u1 by del x3, that is 0 component. Del u2 by del x1, del u2 is this one with respect to x1, that means with respect to x, 2y. Del u2 by del x2 with respect to y, 2x. The next component is del u2 by del x3 with respect to z, that is 0. The next one is del u3 by del x1. Del u3 is this one with respect to x. So with respect to x, 0. Del u3 by del x2 with respect to y, 2z plus 0 because time is not there. Del u3 by del x3, that is this one. So 3 is with respect to z, 2y. This is the velocity gradient tensor. There I need to really apply at 1, 1, 1 kind of components. If I am going to do that, I will get velocity gradient tensor. This is the way we have to work it out. Niranjan, can you shoot a mail to me saying that there is a mistake which I will update and again reshare the notes. Okay, great.
Yes.
Second, I would like to calculate angular velocity of the system. Angular velocity of the system is half of del cross u. So del cross u is up to you how you want to calculate epsilon ijk, or you can bring ijk components del by del x, del by del y, del by del z. 3xy square, 2xy, 2zy plus 3t. So the first component is in between this one and this one. So del by del y of 2zy plus 3t. I think I made mistake here also. I will check it. So first component is del cross product. I need to calculate del by del y of 2zy. So y goes off, 2z survives. The second one minus 0. The second component, I have to flip the sign. So the flipping of the sign means I need to first calculate 3xy squared del by del z. That is 0 minus del by del x of next component 0. The third component del by del x. So that is 2y. Del by del y of this minus 6xy. This is what we call angular velocity. At 111 point, we plug the numbers, we will calculate that. I will update the notes again. Now, I would like to calculate deformation rate tensor. Let us use red color. Deformation rate tensor is half of your velocity gradient tensor del u plus del u transpose. We will see that. Del u is already we know del u by del x 1, del u1 by del x1, del u1 by del x2, and so on, so kind of stuff. Transpose by half. So del u1 by del x1 plus del u1 by del x1 whole by 2 is del u1 by del x1. The second element del u1 by del x2 we have, and transpose element del u2 by del x1. So del u2 by del x1 half of that. Similarly, del u3 by del x1 plus del u1 by del x3 half of that. If we repeat that process carefully, what we are going to get is deformation rate tensor as del u1 by del x1, del u2 by del x2, del u3 by del x3 at the diagonal elements. And off diagonal elements, you always have a kind of repetition. The top one is half of del u1 by del x2 plus del u2 by del x1. Here what we have is half of del u2 by del x1 plus del u1 by del x1. It repeats symmetrically. Similarly, you pick this one. This one repeats here because it's a symmetric matrix. Then this element repeats here. That is the way we calculate deformation rate tensor. Once we calculate that, we plug this xy variable, try to really figure out what is happening. I will check it, the values, and again repost it. Please look at that notes. The next one, if we want to really calculate linear strain rate, as I said, you take deformation gradient tensor, calculate trace value of that, the diagonal elements. That means if I am going to pick this one, this one plus this one plus this one, which is nothing but divergence of u. If you look back, volumetric strain rate, when we have calculated, we got del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3. We got. This is what we call volumetric strain rate. Think of a situation, a box which is expanding, contrasting in such a way that the volume variation is not going to happen. That means x direction, it might be going to expand. This is the box. It expands in such a way that the volume variation is not going to happen. That means x direction, it might be going to expand. This is the box. It expands in such a way that the volume variation is not going to happen. That means x direction, it might be going to expand. This is the box. It expands in such a way that the volume variation is not going to happen. That means x direction, it might be going to expand. This is the box. It expands in such a way that it goes in that way. Volume remains preserved. If that happens, your linear strain rate becomes 0. That is equal to 0, which we call incompressibility condition. But if I would like to really explicitly calculate linear strain rate, what I am supposed to do is calculate trace of the symmetric part of that is half of del U plus del U transpose. This one, what we call linear strain rate. So calculate del U1 by del X1, del U2 by del X2, del U3 by del X3, add them up. Then you will get linear strain rate. Now, if I would like to calculate rate of change of angle between X and Y, you take any fluid element which is governed by whatever those U field which we have learned. The rate of change of angle between X and Y is basically it changes to that, and this one changes to that, and this one plus this one, alpha dot plus beta dot, which from our notes we can see that del V by del Y plus del U by del X. Based on the velocity field, whatever it is given, we differentiate it to calculate what is the rate of change of that angle. There is something named, yeah.
So it is del U by del Y plus del V by del X.
That's right. I'm really sorry. I have to really update that. I'm really sorry. I will check it, Niranjan. It's supposed to be del V by del X, the crosswise components, del U by del Y. I think that is a mistake throughout when I develop the notes. This week, I will carefully see it and cross verify those stuff, update it and post it. Okay. And that is the way we will calculate at math level. There is something named principal strain rate and direction that we will see it in the next class.